talking about the PID controller, so the easiest way to understand what is happening there is to take a look at the proportional mode control. So, and right now we are having such an exercise. So first of all, what do we have? Maybe I do it a little bit deeper. We are having again our tank with some liquid inside, and we are having P control. So what information we get? First of all, we know that our control valve, which can control the input or inflow of the system, it has such low scale factor. This is lambda, which shows that we can have 10 cubic meters per hour per percent of the controller output. So also we know that our controller gain is 10% per percent, and the load change is 700 cubic meters per hour, and initially it was 400 cubic meters per hour. So basically, at the initial position, we had that our output was 40%. So in that case, we should calculate what is the new controller output and what is the offset error. So first of all, please let's take a look at our system, and let's consider what we should have. So basically, we should have that output equals to 700 cubic meters per hour. So how can we obtain such a situation? So basically, we know this scale factor, and we know and we somehow should know the gain of the controller. So basically, that means that we can obtain our our 700 cubic meters per hour multiplied by the lambda and the output of the controller. So for that matter, output of the controller will be 700 cubic meters per hour divided by our lambda, which is 10 cubic meters per hour.
Okay.
10, not 100. So basically that means that we should have 70% of the output in order to keep level of our liquid inside the tank. Otherwise, because loads have been changed, so because load has been changed, in that case, in some time our tank will be empty. So basically, at the beginning our output was 40%, and then we should change it to 70%, or our exit or our tank will be empty. So this is the new controller output. Then we would like to get to know what is the that error. So basically, we know that in order to find out what is the output of the controller, so it depends on the initial situation, and the next, it depends on the gain of the controller multiplied by the error. So that's why it's called proportional. So in that case, if we would like to find out what will be the error, so in that case it will be u minus u0 and divided by the kc. So this is the gain of the controller. So for that matter, our final output is 70% minus our initial 40%, and then we divide by the gain, which is 10% per percent. So in that case, we are having 30% divided by 10% per percent, and you will have 3%. So error of our control will be 3%. So in that case, basically, we can also find out what is the proportional band for our controller. So proportional band, as you remember, I have taught every laboratory work that we have such a dependency. So basically, when we draw characteristics of our controller, it doesn't matter which one. So we have inverse or direct characteristics. So if we have that, basically, if this is direct characteristic, so basically we have such. This is 100%, this is 0%, and depending on what we would like to get, we can have different parameters here. But for example, proportional band is here. So basically, the gain Kc shows what is the angle. So the proportional band and Kc, they are connected with each other. So for that matter, proportional band equals 100% divided by Kc, and in that case, it will be 10% of something. Basically, that means that proportional band, because we would like to control well, so those 10% will be, for example, angle or of our well. For example, if depending on the type of well, so so if this is our pipe, so this is the fully closed position of the well, and we can turn it here, and this is fully open position. So basically, in that case, sorry.
Usually preferences too.
proportional band as 10% of that angle, something like that. Here, such situation, another task, what we have here, for example, proportional mode temperature control. And we would like to find out the situation, how proportional gain.
We can describe this proportional band as a degree, and when we have percentage, then it's 36.
How proportional gain impact our control. So for that matter, we are having such a situation. So for a P, control the temperature of the process varies. The range of 50 to 150 degrees, and set point is set as 80 degrees Celsius. So our initial conditions, output of the controller was 50%. So find the proportional offset resulting from load change if a new output of the controller equals to 60%. And proportional gain is, we have 4 different cases for that. So basically, in that case...
Sorry? One question to this proportional band. Can we describe it also in a slope or in an angle of this 10%, or is it just 10% of our gain? Can we calculate it also in an angle or
for example, here
well, we have 90 degrees and 10% of 360 yes. degrees is 10% of the
full scale.
Of full scale. Full scale.
Yes. If, for example, if we talk about our laboratory works, then we deal with temperature. Mm-hmm. So there we have different types of controllers. In one controllers, we should set a proportional band as in percent. And in other controllers, we should set our proportional band in units which we are using. So in that case, basically, you can find, for example, for the work with motor, actually it matters, because then you set your parameter, you set in percent, and after that, then you find out the characteristics, real characteristics of the process. Then you find it out as degrees Celsius. So for that matter, you just should know the whole characteristics of the process. So for example, for if we know that thermocouple whole range is from 0 to 500 degrees, then 10% will be 50 degrees. If we know that full range is here, for example, 90 degrees, this angle, then 10% will be 9 degrees of that. So basically that means, depending on the set point, our output will be proportional to the error within that 9 degrees of the angle. And before that, we will have full, we will have 100% or 0%, depending on which situation we are. With that situation, basically the first one, what should be mentioned, that we have so-called initial conditions. So at the beginning, then our set point was 80 degrees, we had output of our controller not 0, but we had already 50%. So for that method, this is our set point, and this is output of our controller from 0 to 100%. And so half of that will be somewhere here. So in that case, depending on the gain of the controller, our characteristic will be still here. And for that matter, basically we can find out what is the errors or offsets then we have changed in output of the controller. So this is 15%. So again, so our first error will be so final was output was 60% and initial was 50%. So for that matter we have K. Our first KC equals to and it is percent degrees Celsius. So in that case we have 10 divided by half. So as you can see, if our gain is small, then error caused by such a small change will be 20 degrees Celsius. It's a huge offset. So for proportional band, let's take a look what is the proportional band. So in this case, proportional band will be 100% divided by the gain. So basically, what does it mean? So at the beginning, when we have our initial situation, then if this is 80 degrees, then basically we if this is half of our output, so we would like to have a symmetrical situation. So it will be. And 8, it will be minus 20.
This I want to evaluate. It's 18 degrees. This is minus 20, 21.
So
Can we?
this is 40, this is 20, so
I think. Sorry, can you write the numbers a bit bigger?
which one?
No, the graph. Maximize it a little bit.
This graph.
Yes, the numbers.
Numbers
The
around.
numbers on the graph.
Oh, okay, but it's obvious. So
Yes,
you
I see this, but I can
yeah,
see this graph.
if we have found what is the proportional band. So according to this first game, it should be 200 degrees Celsius. Basically, right now I'm trying to find out the graph of how representation characteristic of our controller. So having such a huge proportional band, basically I just divide it by 2. So because our set point equals to 80 degrees Celsius, so I just add 100 here and I subtract 100 from here. So and that means that our characteristic is like that. So if proportional band
No, it's okay.
is so big, so we just in that case we can control and change proportionally output of the controller to the error in such big area. So from one point this is good, but from the other point it is not so good, because as you can see our offset is huge. So if we take a look at the second case, so for the second case, E2, what we have? We have the same situation. Our output have changed for 10% only, but the gain is 1%. So for that matter, we have error, offset error as 10 degrees Celsius, and for that matter, proportional band will be 100% divided by the gain of the controller, and gain of the controller equals to 1. So we will have only 100 degrees Celsius. So at the initial position, if this is 80, we divide 100 by 2, it will be 50. So 130 somewhere, and then 30 somewhere here. So this is for the second. This is characteristic for the second controller, like that. So our proportional band is much twice less, and this will be 30 degrees, and this will be then
Okay.
degrees. So the
130.
next case, I'm not sure that I have
The first one is 30 and the second one is 130, yeah?
just for the next, the third case, again, 60 minus 50 divided by, what is the third case? We have 2% per degree Celsius. static error. So proportional band for that matter will be 100% divided by the Kc, so divided by 2. So we will have 50 degrees Celsius of proportional band, and this will be then half of that and half of that. So this will be 55. And this will be
105.
105 degrees.
Yeah.
And the last case, error of the fourth controller will be divided by 5. So it will be 2 degrees Celsius.
And the numbers are
In that
70
case,
and 90.
proportional band will be 100% divided by the gain of 5. So we will have
20.
20 degrees Celsius. So
Yeah, 70 and 90.
10. This is 90, and this is 70. So, as you can see, the less is proportional band, the less is error, offset error. But on the other hand, in that case, we will change a little our we will change very fast our control signal, and in that case we can have oscillations during the control. So always you should choose the right parameters, and depending on what what is important to you, do you need the speed of the control, or do you prefer more so to avoid overheating or over control. So in that case, you should use different settings for your controller. So this is it for that part. Please try to find out the solution for the third exercise, and if you will have questions, then you can ask. So let's continue talking about our outputs of the controllers. been on our laboratory works, they already seen that basically even if we controlling just one object or one process, then we still can have such. Then we can still have such a situation. There are several outputs of the controller are used. So the most simple case, then, for example, one output is used as a control signal, and another output is used as an alarm. So in that case, we can provide that information further. But in some other cases, we can use different characteristics or different processes. For example, one of the outputs can be used for heating and one for cooling. Why we need such opposite processes? For example, in some chemical processes, in order to obtain the right product, first of all, we can use the same controller for different types of the processes. One of them is exothermal reaction. There we have a lot of temperature or energy from that process. And another type of processes, they basically take energy or take temperature from the environment. So that means that basically we can use the same controller for both types of processes. But the most useful case, then, for example, we are dealing with some plastic casting and pressing. So here we have just small parts, and we would like to provide that parts to the to other maybe to other parts of our field, so where we can melt it and or extrude them. So basically, in that case, then we have parts from our pump, a pipe here. So we should pull it a little bit. Then we can have the right and flow inside that pipe. But sometimes we can have interactions here. So then there is no material inside the pipe, and we still heating it. So we can have overheating. And those areas can be cooled by the same controller if we have information about that process. So basically, characteristics of the controllers can be the next. So we can have just two outputs of the controller, so the which do not have some overlapping paths. So it's obvious when we've got temperature which is smaller that we would like to have, for example, in this room. So it's then we have low temperature, then we would like to heat. If, for example, our set point is 23 degrees. So if temperature is hotter or higher than 23, so we will cool. But sometimes we can have, for example, overlapping here, and this can be forced. Then we talk not about the heating and cooling, but then we talk about the control of the motors. So basically, if our dead band is small, then we can have a situation. Then our controller doesn't understand in what direction our motor should work. So, or if this dead band is too small, so in that case we can have such a situation. So the rotation of the motor was, for example, clockwise, and after that we need to change the direction of the rotation. And if the deadband is too small, so we can break our motor. So for that matter, it is better to have some deadband between those characteristics. Sometimes we can use even different types of control techniques of the same controller. For example, even the cheapest controllers which we have in our laboratory, they basically have such a characteristic. So first output is PID control. Then we can control, for example, we can heat or we can cool some object. And another on-off controller, this is, for example, alarm output. So in that case, basically we have two different outputs from the same controller. So right now we will talk a little bit about alarm output because you have such a question on your second work, laboratory work. So basically there are several types of alarms, and you should know how to find out about what types we are talking right now. So we can have so-called absolute alarms, then we set just exact values. So for example, I would like to get to know if my temperature is higher than in the room, for example. If temperature is higher than 30 degrees, so something goes wrong with our heating system. So I will have alarm here. I just set 100 degrees to the controller, and then I have that flag that yes, the temperature is outside the limits. And of course, for that matter, we can also set a low level. Or sometimes we have such, in such way we can have both levels. But for that matter, basically, if we use just absolute alarms, then we should have two parameters. This is not so cool and so easy. So for that matter, it is better to use so-called deviation type of alarms. The difference is that we are setting what is the initial value from which we are counting. So basically, as an initial value, we are taking, for example, our set point. So that if we talk about temperature, we just say that our set point is our initial point. From that, we would like to see what is the difference of the present temperature. So we take an error between those. So for example, if our set point is 23 degrees, and I would like that I have some notice if temperature is higher than 30 degrees, then I should set deviative type alarm at 30 minus 23, which will give me 7 degrees. So basically, then I will just set the difference between those limit set point and the limits which I would like to use. And in that case, for example, if I have such type of alarm, so I can manage the same value for the both levels, higher and lower level. So as an initial value, we should use some parameter from our process. And of course, we also can have because this is basically works as an on-off signal. So we also can have such characteristics for the alarm systems as a hysteresis. So in that case, it will prevent the rapid changes for our of our signals, because sometimes it's if we are dealing with a huge process, for example, in some power stations, so we would like to get to remember, for example, that something happens. So of course we can some log files where we can see the history, but this window which shows that we have not so ordinary situation, extraordinary situation. So we can use such alarm as a memory. So we will remember that we had something bad during some time, and after that our window will be erased from operator's work desk. And let's now talk about the real outputs of the controllers, what you will deal during our laboratory works. So basically, we just talked about the different types of the controllers and how we can mix them. And right now, one of the output of the controller which is used in our laboratory is PID controller with analog output. So basically, as you remember, then I talked about the signals, different signals which is used in industry. So one of the widespread signals is current from 4 to 20 milliamperes. Also, it is often used signal from, for example, 0 to 10 volts, or from -10 to 10 volts. But in our laboratory we are having such a controller. So in that case we can use such an output in order to control different types of actuators. Basically, for example, in our laboratory we are having thyristor type Y30. So knowing the output of our controller, we can set different RMS values for the voltage from 0 to almost 200 volts. Also, such kind of controllers can be used in order to position our motor or other systems. So we can control positioner knowing the whole range of the actuator, and also some using some frequency converters in order to control drives. So in that case, output of the controller can be given both in percent or just in the units which we have in our application. So basically, a little bit more I will talk then when we will talk about the linearization of the process. So another type of the controller which is used in our laboratory is so-called PID controller with relay output. What is the difference? So if we are dealing with analog output PID controller, so that means that we can have our signal from the whole range. So from the 0 to 100%, and each value can be obtained. But if we are using pulse output, so in that case, basically, if we are dealing with relay, so in that case we can have just 1 or 0. If we have contacts which are connected, so we have 1 or 100%, and if we don't have a contact, so we have 0. So for that matter, how can we manage the situation then? Then we would like to control, and for example, in our control action, we would like to obtain output equal to 70%. So in that case, we should use such called technique, pulse width modulation. So with that technique, we always have such a parameter, or this is time during which we are observing our signal. So in our case, in our on-run controllers, this is called CP, or control period. So this is the period of observation here. And also we have another parameter, this is pulse width. So basically, during this pulse, we are having 100%, and so depending on the width of that pulse, we can obtain a value which we would like to obtain. So basically, if we would like to obtain 70% of the output of our controller, that means that during this CP control period time, 70% of the time our output will be 100%, and only 30% of the time we will have 0. So basically, there is two cases where we can consider that situation. So they are opposite situations. Basically, in that one case, we can change the pulse width, and then this control period will be set by you. For example, in our laboratory work, in one case you set it, for example, for 5 seconds. So during this time, during 5 seconds, we will observe the output, relay output of the controller, and manage the width of this pulse. But there are some other types of controllers. There we can manage this parameter, but pulse width will be constant. So for that matter, please always check the vendor specification where you can see and set the right characteristics. Otherwise, you can have a trouble during your control. So, in case of PID control, as I told you, we are having this CP parameter. So, for that matter, with the same period, we will have different width of the pulses here, and basically we can obtain the right output of the control. So this will be the mean value of the output. Why we should use so for these parameters from 2 to 20 seconds, this range is used basically for our object which we have at our laboratory. But for example, if you are dealing with real buildings and you know that thermal processes, they are very inertial, so first of all you should take a look how changes in the input, then you change the, for example, power which is given to in order to obtain high temperature in the room, and the result, then your actually temperature of the room will change. So in that case, CP parameter can be maybe 24 hours. And why we should use such kind of technique? Because first of all, when if you take a look just for one of the vendors' sites, you can see that difference in the cost is quite big. So if we would like to obtain just analog output controllers, then we should pay much more than we obtain such controllers with relay output. So this is simple and cheap, and for that matter, first of all, we need to check so that object's time constant, which can be obtained by you through some experiments or just from writing down the physical laws, and after that you can obtain the transfer function. So we should take a look and check that our object time constant is much more larger than this parameter which is called CP in our controller. So for that matter, we will obtain quite a good situation. Otherwise, if time constant of the object is almost the same as the CP parameter, in that case, you will have almost the on-off situation. So you will have oscillation during the control. That's why you should always take a look and set the right CP time for your object. And if time constant is much more larger than the period, observing period, so in that case, pulse signal doesn't pass through the object, and in that case, we will have such a beautiful picture. So our control will be just pure P control with good line. So our line will be straight, not oscillating. So and for that matter, basically another good reason why we should use that, because using such a technique we can linearize controlled object. Why is that? Because we know that if we talk about the temperature, if we would like to control temperature, and we know what is the voltage from our object, then you know that dependency between those, as you have found from our first laboratory work, is it depends on the initial temperature plus some coefficient which is concerned to the object. So it depends on the material which is used, and this is RMS value. For that matter, you can see that temperature do not depend linearly from our voltage. So it's not good to control such a dependency, because we have non-linearities, and that means that we face difficulties. So it's much more easier to control when we have linear dependency. So for that matter, control by power is much more better, because basically in that case we will have just linear dependency between the power and the output of the controller. So it will be proportional to the output of the controller, and in that case it is easy to calculate what should be output of the controller and what should be the power. Another type of a controller which is used in our laboratory is so-called position proportional controller. We are dealing with floating control with our motor, and why we should use such a strange technique. There we are, first of all, we are using a free positional controller with our hysteresis and deadband. So if you remember just floating control, so during that floating control we can describe it like that. So we have three positions. First position, there nothing happened, our motor doesn't work. Then rotation to one position or another position. So basically, because of the hysteresis, you can have such a situation here. And this is deadband. This is deadband, and this is hysteresis. So basically, if error is small and it remains within that period of deadband, then nothing happened, our motor stays. And then if our error goes further, then our motor tries to moves and tries to set our error to that diapason, to that range. So in that case, we can consider it just prepositional controller. But in that case, it is very hard to control our object, and further slides will show you why. So if we took a look at the situation, so we have 3 operational modes here. Then our speed is positive. We're always moving to the same speed on the one direction or other direction. So we have feed forward, or positive speed, feedback of negative speed, and so another direction of the rotation. And we can stop position. So if we take a look at this situation, so our control mechanism keeps that output y on desired value x, but because of the inertia of the motor, and because of the deadband which we have here, so we never can have the exact position of the motor that we would like to obtain. So you should understand, so because we have this zone, so we always have some difference between the desired signal and what we have in real situation. And the difference will be the half of the dead zone. So you can ask, or you can say, so if we have such an error, it's good, then dead band is very small. In one case, yes, but on the other hand, if dead band is very small, so in that case we can have a situation that our motor starts to rotate from one direction to another very fast, and it will be broken very soon. So that means that sometimes we should consider which case is better for us. And that's why, for example, from the whole range, dead band always a little bit bigger than this hysteresis, or at least the same. So if you continuously change your signal, so in that case we can have such a situation. If we change the set point, then the real values of the position can be seen here. So first of all, if we move on one position, then the difference will be positive. But if we change the direction, so for example, right now we would like to open our valve, and here we would like to close it on the other direction. So you can see that error changes its sign. If we talk about the motor, so the main parameter for that motor is the motor travel time. For those of you who have done work number 4, they already met that parameter. So basically, motor travel time, this is the time then our motors goes from the fully open to the fully closed position. So it's a time which can be taken by motor from one position to another. And knowing that parameter, we can already say what will be the speed of the control, and what should be how pulse length here depends on the basically on the motor travel time. So in that case, we can calculate what will be that length of that pulse in order to obtain position, right position for our valve. So knowing the difference or changes of the output.
Sorry? Can you this motor parameter is in seconds, but where's the speed coming? Okay, we have the distance in between this increment.
Yes, speed. The speed is coming depending on what you would like to get. So basically, we.
But what is it? Is it in some volt, or when we apply it to some actual case?
It depends what speed always the work done through per some time. So here we have just the full range in percent. If you know the angle, so it will be angle.
The full range in motor travel, or
yes, the full range. So for example, then we discussed that situation that we have valve which closes and the pipe. This one. So it can be rotated. This is the fully closed position, and this is fully open position. So in that case, our 100% will be angle of 90 degrees.
okay, yeah, okay. Then it's somehow still away, or angle away. Yeah, okay. It's just a bit confusing, this unit.
So here we have initial position plus half of the dead band and the next position what we have. Actually, I can't understand why this projector can't show the full format of my display.
I think there is an option that fits screen. I think.
Yeah, better next time.
Okay.
I have